In our last video for our first chapter, we are coming back to the special case of resonance. After a brief introduction, we're going to talk about the rules and reality, and we'll look at how to draw resonance structures and the resonance hybrid. Early on in this chapter, we were talking about how to draw Lewis structures, and we saw that for the carbonate ion, we could actually draw three different Lewis structures. We could have the double bond here, or here, or here. We would have two lone pairs, two lone pairs, two lone pairs, three lone pairs, and a negative charge, three lone pairs, negative charge, three lone pairs, negative charge. The fact that this Lewis structure is drawn with a double bond and single bonds, this suggests that there will be different bond lengths, a shorter C double bond O and a longer C single bond O. But experimentally, all of the CO bond lengths in carbonate are the same. All CO bond lengths in carbonate are the same. So this Lewis structure is not an adequate picture of what must actually exist. And we said that what exists is a resonance hybrid. So rather than just having this structure written, this structure written, this structure written, we would connect them by a resonance arrow. And this says that these are different resonance contributors, and therefore what actually exists will be the resonance hybrid. And that will have the three bonds to oxygen as well as partial double bonds between the carbon and the oxygen. There will be a partial negative, and partial negative. We could be more specific. Notice that this oxygen has a negative charge in 2 out of the 3 resonance contributors, so we could alternatively call this a negative 2/3, negative 2/3 on all of the oxygens. So we are allowed to draw individual Lewis structures, though we need to consider the fact that each of these is really incomplete and that what actually exists is the resonance hybrid. It's also important to keep in mind, we are not talking about this species changing to this species changing to this species. If you were able to take a photograph, you're not going to see this and then this and then this. Instead, you're going to see none of these because every single molecule is going to exist like this, with the electrons spread out evenly between each of the carbon-oxygen bonds. Resonance refers to the delocalization of electrons, which leads to a special stability. The delocalization of electrons leads to a special stability. And we can think about this special stability because the electrons are attracted to more nuclei. And whenever you have a charge, that charge is going to be spread out. And if you have the option of a concentrated charge or a charge that's spread out, then the molecule will be much more stable with that charge spread out. Now, to be able to have resonance, one requirement is that you must have p orbitals, because resonance occurs through a pi system. Now, what are some features of molecules that undergo resonance? We have to remember that the Lewis structures that we draw are imaginary, and the movement of electrons that we show as we're drawing multiple resonance structures, that is also imaginary. Individual resonance structures differ only in the placement of electrons. If a hydrogen is in a different place, then we're not talking about resonance structures, we're actually talking about isomers. So it's only the difference in the placement of electrons. The different resonance forms or resonance structures are not necessarily equivalent. In the case of carbonate on the previous slide, each resonance structure had one carbon-oxygen double bond and two carbon-oxygen single bonds. So those three structures were equivalent to each other, but that's not always the case. Resonance forms obey rules of valency. So each resonance structure must be a valid Lewis structure even if it's not a sufficient representation of what actually exists. So, for example, we can't have 5 bonds to carbon. We still have to remember that carbon likes 4 bonds and oxygen likes 2 bonds and hydrogen likes 1 bond. We still have to have the correct number of electrons overall. So our individual resonance structures or resonance forms must be good Lewis structures. And then another important feature when we're talking about resonance is that the resonance hybrid is more stable than any of the individual resonance forms if they existed. So there is an advantage to existing as the resonance hybrid. In addition to these features of resonance structures, let's also include here a brief list of how-to. So when it comes to drawing resonance structures, we need to make sure that we only move electrons, and that movement is in quotes because it is the imaginary movement of electrons, but we're only moving electrons, not atoms. Each resonance structure must be a valid Lewis structure. So this goes along with the feature number 4. Equivalent resonance structures contribute equally to the hybrid. And then more stable resonance structures contribute more to the resonance hybrid. So there's a problem with that sentence because the more stable resonance structures, but the resonance structures don't exist. So how can we compare their stability? That's a problem, but we need to think about different features. So if the resonance structures are equivalent to each other, then that's pretty easy. We're looking at just the average. If the resonance structures are different from each other, then we need to think about a weighted average where the more stable resonance structure would have more covalent bonds, would have everybody obeying the octet rule, it would have less charge separation, or it would have a negative charge on a more electronegative element. So these are some of the features that we would be looking at to try to determine which resonance structure, if it existed, would be more stable. So let's try this out on the next slide. So let's start out with carbonate. And if we are starting here with this particular resonance structure, how would we get to another one? Actually, before we do that, let's think about what are we looking for. So the fact that we have a pi bond and we have extra electrons, then that will allow us to have the delocalization of electrons. This also necessitates having sp2 hybridized atoms so that we can have a p orbital. Right? We already said if we looked at this, because it's connected to 1, 2, 3, 4 groups, we would expect this to be sp3 hybridized. But if instead it took on sp2 hybridization, then that would have a p orbital that would be able to be involved in the delocalization of electrons. So if we're trying to draw a resonance structure from here, because we are starting with a negative charge, let's imagine that these electrons move away to lose that negative charge. So these electrons would move here. And notice I'm using the dotted line because we're talking about imaginary movement of electrons. And these electrons would have to move up here. And so we can draw another resonance structure where here is our negative charge, here is our double bond, and here we still have our single bond. Oops. Then we can draw another resonance structure. Let's imagine that these electrons move here to form a double bond, pushing these electrons up here onto the oxygen. So that gives us a third resonance structure. This one hasn't changed. Here, we now have our negative charge, and this one is our double bond. So we have drawn our three contributors where the double bond is up, the double bond is to the right, or the double bond is to the left. Now, to draw the hybrid, we're going to take the average of all three of these. So the resonance hybrid just looks like this. Partial minus, and partial minus. Now for our next example, we have C6H6. This is benzene. And this exists as a six-membered ring where each carbon is connected to one hydrogen, and we can draw this with alternating single bond, double bond. All of these carbons are sp2 hybridized, which means we have the p orbitals so that it's possible for the electrons to be delocalized. Well, let's draw another resonance structure, but to get there, we want to imagine that these electrons move here, the same time as these electrons move here, the same time as these electrons move here. So our other resonance contributor would have a double bond here, a double bond here, and a double bond here. Experimental evidence shows that in benzene, all of the carbon-carbon bonds are equivalent length, so they do not exist as a single bond and a double bond. They exist all as a 1.5 bond. So our resonance hybrid is going to look like this, where we have partial double bond character all the way around the ring. In our next example, we have CH3. This must be a double bond O connected to a CH2, and this carbon has a lone pair and a negative charge. So to draw another resonance structure, this carbon must take on sp2 hybridization to have a p orbital so that these electrons can be delocalized. And again, because we have a negative charge, let's start with these electrons and move away. We don't want to try to move our electrons toward a negative. Let's try to move them away. So these electrons can go here, pushing these electrons up here. So that gives us another resonance structure where we have a single bond to oxygen and a double bond to the carbon. Unlike what we saw with carbonate or with benzene, these resonance structures are not equivalent to each other. Here we have a double bond to oxygen, here we have a double bond to carbon. Here we have a negative on carbon, here we have a negative on oxygen. So which one of these, if it existed, would be more stable? We have the same number of bonds. Everybody obeys the octet rule in both of them. Really, the biggest difference is that we have a negative charge on carbon compared to a negative charge on oxygen. Oxygen is more electronegative, so this is going to be the major contributor. So rather than drawing our resonance hybrid like this with equal double bond character and partial minus, partial minus. That's okay, but it would be more meaningful if we tried to draw it more as the weighted average, where this one is the major contributor. So we have significant double bond character here and a lesser amount of double bond character between the carbon and the oxygen. And then we have big partial negative charge on the oxygen and small partial negative charge on the carbon. So we need to draw our resonance structures and then evaluate the resonance structures. First of all, we need to evaluate them to make sure that each one is a valid Lewis structure, but then we need to think about the relative stability, because this one, if it existed, would be more stable, then it is going to be the major contributor. So while the hybrid looks like something in between these two, it's going to look a little bit more like this one than this one. And that's what I've tried to represent here. And here we have a few more examples. So our first example, we have CH2, which must be double bonded to the CH, which is then single bonded to the CH2. This carbon has a negative charge, so it must have a lone pair, which would give this carbon a formal charge of -1. Because we are starting with a negative charge here, let's try to move our electrons this way. So we'll go from the lone pair to the bond. So we'll imagine that these electrons move here, and at the same time, these electrons will have to move onto the carbon, giving us another resonance contributor, where here we have a lone pair and negative charge on the carbon. This is now a single bond, and this is now a double bond. So these resonance structures are equivalent to each other. So the resonance hybrid would look like this. Partial double bond character here, partial double bond character here, partial negative on this carbon, and partial negative on this carbon. If we look at our next example, we are again starting out with CH2 double bonded to CH, single bonded to CH2, and now we have a positive charge on this carbon. Up here, we moved our electrons away from our negative charge. So here, let's try moving our electrons toward the positive charge. So let's imagine that these electrons move over here, and that will give us a second resonance structure that looks like this. Here we have a double bond, and now this carbon has a formal charge of +1. Once again, these resonance structures are equivalent to each other, so they will contribute equally. So our hybrid is going to look like this. Our CH2 connected to our CH connected to our CH2, partial double bond character here and here, a partial positive character here and here. Now, in our third example, we have a radical. We have an unpaired electron. So we can draw this as CH2 double bonded to CH, single bonded to CH2, and there is an unpaired electron on the carbon. Now, to draw our resonance structures, we have to imagine the movement of a single electron. So first of all, this is where we use the single barbed arrow. And this also is going to look different in terms of the movement of electrons. Notice up here where we move two sets of electrons, the arrows were both going in the same general direction, so it's like we're going downstream. But it's going to look a little bit different when we're talking about radicals. So here we imagine that this electron moves here toward the bond, and then out of this pair of electrons, one of them is going to move over here as well to be the second electron in a new covalent bond, and then the other electron of this pair is going to move onto this carbon. So our other resonance structure has the CH2 single bond, CH double bond, CH2, where this is now a radical. All right, so out of this pair of electrons, one of them is now here, and one of them is now involved in this double bond, and then this electron is also involved in that new double bond. And when it comes to a radical, this is where it's a little bit harder to draw the hybrid. This part is the same, so our CH2, CH, CH2 with partial double bond character, but this is where it gets a little bit weird. We could do like a partial radical, that's okay with me if that's the way that you draw this. So a few more examples, and we walked through how to go from one to the next one to be able to draw additional resonance structures. And then once we have our multiple resonance structures, how do we draw our hybrid? One other thing I wanted to point out, notice even though we're talking about the imaginary movement of electrons, I use this arrow to represent the movement of electrons. I use this arrow to represent the movement of electrons. And then once the electrons were in their new locations, that's when you calculate the formal charge and find that this carbon now has a negative charge. We never draw arrows to and from a negative charge or here to and from a positive charge. Arrows are not used to represent the movement of charges. Curved arrows are used to represent the movement of electrons. And then after that movement happens, the charge is what results. Right here, we moved these electrons, and this carbon, which only had 1, 2, 3 bonds, and therefore it had a formal charge of +1, now it has the 2 bonds to hydrogen and 2 bonds to carbon. So now this carbon has an octet, and it does not have a formal charge. This is the one that has the formal charge. So we use the arrow to represent the movement of electrons, and then the charge results. So from here, it's important that you keep practicing to draw additional resonance contributors as well as the resonance hybrid. And with this practice, you'll also gain experience in identifying molecules that can be stabilized by resonance.